What if I told you that the object sitting quietly in the corner of a hospital room, the one most people walk past without a second glance, is one of the most precisely engineered pieces of equipment on the planet? We're talking tolerances tighter than a Swiss watch, materials refined to 99.9% purity, and a manufacturing process so demanding that a single gram of excess weight can change someone's entire life. Today, we're going inside the factory where wheelchairs are born, and nothing about this journey is what you expect. There are over 130 million people in the world who depend on a wheelchair every single day. That's more than the entire population of Japan. And yet most people have no idea that a single modern wheelchair can contain up to 200 individual components, travel through 7 countries before it's finished, and cost anywhere from $200 to over $50,000 depending on the engineering packed inside it. We are about to pull back the curtain on all of it, from the raw earth it comes from to the moment it rolls off the line. But here's what nobody tells you. Building a wheelchair isn't just an engineering problem. It's a human problem. Every angle of every tube, every millimeter of every seat frame, it has to work for a human body that's counting on it with every breath of every day. And the moment something goes wrong, someone pays the price. That pressure is what drives this entire factory. Stay with us, because what happens in the next 15 minutes will change the way you see this chair forever. Every wheelchair begins not in a factory, but in the ground. The 2 dominant materials used today are aluminum alloy and titanium, and getting them to a factory floor is an epic journey all on its own. Most of the aluminum used in wheelchair manufacturing originates as bauxite or strip mined from deposits in Guinea, Australia, and Jamaica. Guinea alone holds over 25 billion tons of stuff, roughly 1/3 of the world's known reserves, and every year, tens of millions of tons are blasted out of the Earth's red clay surface. That raw bauxite is then shipped to smelting facilities, many located in Iceland, Norway, and Canada, where cheap geothermal or hydroelectric power makes the energy-hungry refining process economical. Here, bauxite is crushed, dissolved in caustic soda at temperatures of 150 degrees Celsius, that's 302 degrees Fahrenheit, and spun in enormous pressure vessels to extract alumina powder. It takes roughly 4 tons of bauxite to produce 2 tons of alumina. And that alumina then gets electrolytically smelted at 960 degrees Celsius into the liquid aluminum that will one day hold a human being. Premium wheelchairs, the kind built for Paralympic athletes and high-performance users, skip aluminum entirely and go straight to titanium. And if you think aluminum has an interesting origin story, titanium will absolutely blow your mind. Most of the world's commercially pure titanium comes from ilmenite and rutile mineral sands, mined along the coastlines of Australia, South Africa, and Mozambique. These beaches look perfectly normal, until you run a magnet through the sand and watch it turn black. The titanium-bearing minerals are magnetic, and they cling in dark streaks that miners collect by the millions of tons. From the beach, those sands travel to processing plants in the United States, Japan, and Kazakhstan, where they are converted to the Kroll process into titanium sponge at temperatures exceeding 800 degrees Celsius. The result is a porous, silvery mass of nearly pure titanium, grade 3 and grade 4 alloys reaching purities of 99.5 to 99.9%. A single kilogram of finished titanium tubing for a wheelchair frame can cost $80 to $120, which is why a lightweight titanium chair carries a price tag that makes your eyes water. But the performance it delivers? That's where the story gets extraordinary. The third critical material is fabric, specifically high-tenacity nylon and ballistic-grade polyester used for seat slings and back supports. These fibers are synthesized from petrochemical precursors in plants across South Korea, Taiwan, and Germany. The yarn is spun to tensile strengths exceeding 800 newtons per centimeter, strong enough to support a 150-kilogram person, with a safety margin that engineers quietly call the dignity margin. Because a seat that fails mid-use isn't just a product defect, it's a catastrophe. And that's exactly why what happens next in the factory is unlike anything you've seen before. When the raw aluminum alloy billets arrive at the wheelchair factory, typically in 6-meter lengths, weighing 25 kilograms each, the first thing that happens is something almost violent. CNC tube bending machines clamp each billet and begin cold forming it around precision mandrels at pressures up to 2,500 psi. The machine works at a speed of about 2 seconds per bend, and the sound it makes is a deep, resonant clunk that you feel in your chest as much as you hear it. Inside the metal, something extraordinary is happening. The crystalline grain structure of the aluminum is physically deforming, which actually makes the finished tube stronger, not weaker. After bending, the tubes are cut to exact length using cold saw cutting machines spinning at 1,200 revolutions per minute. Each cut must be accurate to within 0.1 millimeters, a tolerance thinner than a human hair. Workers in safety goggles feed the tubes in from one end, and the finished sections come out the other side, trailing thin metallic ribbons of shaved aluminum. A sound like tearing silk, followed immediately by the sharp smell of hot metal, and you can feel warmth radiating off each cut surface from just a foot away. Now comes the step that most people never think about, but that defines the entire strength of the wheelchair: TIG welding. Tungsten inert gas welding, to be precise. A skilled welder. And in this industry, skilled is a word that deserves enormous respect. Guides a tungsten electrode along each joint with hands so steady it barely seems human. The arc temperature reaches 6,000 degrees Celsius at its hottest point, that hotter than the surface of the sun by a factor of nearly 1. A protective argon gas blanket flows over the weld pool at 8 to 12 liters per minute, preventing oxidation and keeping the joint pure. The weld joints are completed at a rate of roughly 1 joint every 90 seconds, and each completed frame will have between 18 and 26 individual weld points, each one scrutinized later under a 10x magnifying loupe and an ultrasonic probe. But welding is only half the story of the frame. After all the joints are complete, the entire aluminum frame goes into an industrial heat treatment oven at precisely 177 degrees Celsius. That's 351 degrees Fahrenheit. For exactly 6 hours. This T6 age hardening process rearranges the microscopic alloy particles, increasing the frame's yield strength by up to 60% without adding a single gram of weight. While the frames are hardening, the wheels are being built in a completely separate part of the factory, and this process is its own universe of precision. Hand wheels for manual chairs typically have 24 or 28 stainless steel spokes, each one tensioned to exactly 100 to 120 newton meters using a calibrated spoke tension meter. A single spoke, even slightly out of tension, will cause the wheel to track crooked, which doesn't just make rolling harder. Over time, it destroys the rim. Experienced wheel builders can hear when a spoke is wrong. They pluck each one like a guitar string and listen for the pitch. The tires, either solid polyurethane for indoor chairs or pneumatic rubber for outdoor use, are mounted and pressure inflated to 80 to 100 psi for pneumatic models. The polyurethane solid tires are pressed onto rims and hydraulic presses, exerting 4 tons of force over a 30-second press cycle. And then comes the moment the frame and wheels finally meet final assembly. Workers hand install each axle, footrest, armrest, and seat with torque wrenches set to specific Newton-meter values for every single fastener. Because in a wheelchair, there's no such thing as a bolt that's good enough. But even with all this precision, something shocking still slips through, and the quality control team exists precisely to hunt it down. Most people imagine wheelchair factories as quiet, careful, almost clinical places, and some parts of them are. But walk into the testing lab, and the word that comes to mind is relentless. This is where robotic testing machines simulate years of hard use in just 72 hours, and where every wheelchair that enters has to survive or it never ships. The ISO 7176 standard, the international benchmark for wheelchair safety, requires that every chair pass what engineers call the double drum test. The chair is loaded with a weighted dummy equivalent to 100 kilograms and then driven over 2 rotating drums covered with irregular wooden slats, simulating rough pavement. It must complete 200,000 cycles without any structural failure. Alongside the drum test, load-bearing structures are subjected to static force testing, where hydraulic rams press down on seat frames, footrests, and armrests at forces up to 1,300 newtons. That's roughly the equivalent of 130 kilograms pressing down on a single point, held for 60 seconds per position per ISO protocol. The measurement equipment, records deflection in increments of 0.01 millimeters. Engineers watch the digital readout with the same intensity you'd expect in an aircraft component lab, because to them, that's exactly what this is. But the most extraordinary technology on this factory floor isn't testing machines. It's a 3D laser scanning system that captures the geometry of every finished frame in 11 seconds flat. The scanner shoots 2.5 million data points per second, building a complete digital twin of the frame in midair, and compares it in real time against the C master file to tolerances of 0.05 millimeters. Any deviation triggers a red alert. The rejection rate for frames failing the scan? Just 1.2%, which sounds reassuring until you do the math. In a factory producing 500 frames per day, that's 6 frames pulled off the line every single day for being a fraction of a millimeter out of specification. Power wheelchairs, the electric-driven models, carry an entirely different layer of quality control. The onboard electronics, motor controllers, and joystick systems are tested in climate chambers where the chair is cycled between minus 20 degrees Celsius and 60 degrees Celsius while being powered on and running. This thermal cycling test runs for 48 hours continuously. Joysticks are tested for 500,000 actuation cycles. Battery packs are charged and discharged 1,000 full cycles before approval. And through all of it, there is one check that no machine can perform, and it happens at the very end of the line. A senior QC technician, always a human being, never a robot, sits in the finished wheelchair and drives it. They run it forward, backward, spin it left and spin it right. They load it against a ramp. They sit in it in silence and feel for vibrations, hear for clicks, sense for any asymmetry in the way it rolls. After 20 years in the role, these technicians carry a library of feel in their hands and spine that no sensor array has ever matched. And when one of them stands up from a chair, crosses their arms, and shakes their head, that chair comes apart right there on the factory floor. No argument. No second opinion needed. Here's a number that will stop you cold. The global wheelchair market is currently valued at over $6.8 billion per year. Not billion, over a decade. Billion per year. And that number is climbing fast. With global aging populations accelerating, the market is projected to exceed $11 billion by 2034, a growth rate of nearly 5% per year that makes it one of the most resilient manufacturing sectors on Earth. Think about that for a moment. This industry doesn't have bad years the way auto or electronics industries do. The demand is built into human biology. Approximately 131 million wheelchairs are needed globally right now, but only around 20 million are produced annually. That gap represents 111 million people without adequate mobility equipment. The top producing countries are China, which account for roughly 60% of global production by unit volume, followed by the United States at around 15%, Germany at 8%, Japan at 7%, and Canada at 4%. China's dominance in unit volume is extraordinary, but the United States and Germany dominate the high-value custom and power wheelchair segments, where a single chair can take 40 hours to build by hand. The modern wheelchair industry employs approximately 350,000 workers globally, from miners and smelter workers to C engineers, TIG welders, and physiotherapy consultants who advise on seating geometry. And the history of this industry is far older and far stranger than most people realize. The first recorded purpose-built wheel mobility device dates to 1595, a chair designed for King Philip II of Spain, fitted with wheels and leg rests. For nearly 350 years after that, almost nothing changed. It wasn't until after World War II, when veterans returning with spinal cord injuries demanded better, that the modern wheelchair was born. Did you know that the first folding wheelchair, the X-frame design that most people picture today, was invented in 1933 by Herbert Everest and Harry Jennings? Everest himself was a paraplegic mining engineer, and he designed the chair because he wanted to be able to fit it in a car. That single invention created an entire industry. Did you know that the average manual wheelchair weighs 16 to 18 kilograms? But the lightest production wheelchair in the world today weighs just 1.6 kilograms. That's lighter than a standard laptop. And did you know that in Antarctica, wheelchairs are among the most stress-tested equipment brought to research stations? Because the engineers say if it survives Antarctica, it will survive anything? The future of wheelchair manufacturing is moving at a pace that would astound the engineers of even 10 years ago. Carbon fiber frames, once reserved for Paralympic athletes, are now entering mid-tier production thanks to automated fiber placement machines that can lay a carbon frame in 22 minutes. AI-driven custom fitting systems scan a user's body with LiDAR sensors and automatically generate a bespoke frame geometry in under 4 minutes. And 3D printing of titanium structural components, once a laboratory curiosity, is now being used by at least 6 major manufacturers for production parts. Within 5 years, the wheelchair you roll out of a clinic may be designed, built, and fitted in a single day. We started a day in a mine in Guinea, in the black sands of South African beach, in a petrochemical plant in South Korea. We watched liquid metal become tubing become a frame, and a frame become something that will carry a human being through every moment of their day. We saw machines perform tests that would destroy lesser engineering. We saw a welder hold a torch at 6,000 degrees Celsius with hands that don't shake. And we saw one human being sit in a finished chair, close their eyes, and decide whether it was good enough. What strikes you, if you spend enough time in this factory, is the weight of what's being built, not in kilograms, but in consequence. Every chair that leaves this floor is going to someone whose world depends on it. Someone who will push those wheels 2,000 kilometers a year. Someone who will eat, work, love, and live from that seat. The engineers know this. The welders know this. The quality control technicians who sit in the finished chair and feel for what the sensors can't find. They know it better than anyone. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.